And we're back. Welcome back from the weekend and happy Tuesday. Today we will continue and finish up our discussion of max entropy ensembles. Administrative, we have this paper that I wrote when I was in graduate school. This is the subject of the work today. Also, it's a way of introducing ensembles. And so where we last left off, we talked about negative correlation learning. And in this, I reproduced an experiment that was published, built a multi-layer perceptron ensemble, where the outputs of these perceptrons were voted using equal weights to select one of two different categories for a classification problem. And what I found, as the number of epochs increased, the covariance got more and more negative. And since correlation is just the covariance scaled by the standard deviation, so too does the correlation get more and more negative. And what does this mean? It means that the outputs start to separate from one another more and more over time as it trains. And this coordination, the separation of outputs of the component perceptron networks, is due to the fact that they can coordinate with one another because they are trained collectively. They're trained together. So let's take a look at the DISCO framework, discrete instance selection and collective optimization, which is the name of the algorithm I created. And so in collective ensemble construction, we treat the ensemble as a type of dynamical system, control system, and we have our ensemble model, which is our system under control, our plant, and that is represented by a set of functions representing each one of those component classifiers, many of them in the ensemble, parameterized by this parameter vector consisting of the aggregation of the parameter vectors of all of the component classifiers in the ensemble. And so we have our controllable degrees of freedom, and this will be the instance selection on which these component classifiers will train. Now, of course, they vote, and the output of that vote is your class label. You compare that to ground truth to give you some error. This error is fed back in. That's one aspect of feedback to the system, compared with zero because you want a goal of zero error. And that difference is used to guide the selection of the component classifiers. The other aspect of this is we take a measurement across the component models in the ensemble, and we feed back that measurement, comparing it against an objective, and use that as a secondary criterion with which to find the notional best component classifiers. Now, when you train them collectively in this fashion, you can make trade-offs between the component classifiers instead of maximizing their respective in-sample errors. So you can make suboptimal decisions in service to the aggregate output resulting from the vote. And so let's take a look at ensemble parameter space from the perspective of the instance selection as a type of controllable degree of freedom, because the instances you use to train on are going to impact the resulting parameterization parameter vector for your final best hypothesis. So we have our instances. We evaluate those instances with our component classifiers, we vote, and we get some model parameters out of it. So each model is a component classifier, and our degree of freedom are the training instance selections. And this training results in a change in the model parameters. If you change the training instances, if you retrain, you're going to change the resulting final best hypothesis model parameters. So let's build a data structure. I call this a selection table. And across the rows, we have each of the instances in your in-sample data. So this is our data set here, our data set. So we're going to have n many of these data instances for each row of this selection table. And then there's an entry for each column for each of the m many classifiers in your ensemble. So this is going to be m many columns. And so our selection table is going to be n rows, where n is the number of instances, by m columns, where m is the number of classifiers in the ensemble. And so we're going to depict then the instance selection for our classifiers for training based on this idea of majority voting. Now, of course, if you're going to vote, you need at most, or ceiling of m over 2, more than half, simple majority, correct votes for each instance. And so if you have, for example, 3 classifiers in an ensemble, F1 hat, F2 hat, F3 hat, you need at least 2 correct votes. It could be F1 and F2, F1 and F3, F2 and F3. You need 2 correct votes on each instance in order for this ensemble, this 3 ensemble, to be correct. So this also means you can tolerate some number of errors. You can tolerate floor of m over 2 errors for each of the instances that is input as your training set. Now, of course, when you train on an instance, you're changing the decision boundary associated with each of the component classifiers in effort to get that classification correct. And so you can tolerate floor of m over 2 errors on each instance and the ensemble is still correct in its vote. So let's define something I call a selection table. And in the selection table, I'm going to put little markers here, these asterisks, the don't care markers. And this asterisk is going to be used to mark that floor of m over 2 many errors that you can make in the ensemble of m classifiers, and it can still be correct as aggregate voting output. And so I take this selection table. In this example, it's a 3 ensemble. So floor of m over 2, floor of 3 over 2, that's going to be 1. So we can tolerate an error in one classifier in a 3 ensemble, and it still is correct. And so in this selection table, we're going to put an asterisk, and that's going to be a marker that represents the errors associated with the ensemble. Now, we don't know which of the classifiers is going to be wrong, but we know that one of them can be wrong, and the ensemble is still correct if it's a 3 ensemble. And so everywhere else, we're going to put a 1. And this marker, this don't care marker, I'll call it, is going to represent what I'm going to call the error budget. How many errors the ensemble of 3 classifiers in this case can afford. And so this selection table, if I do that for every row of the table, you'll notice I only have a single don't care marker for each one of the rows representing the error budget. And so now let's imagine this marker can be moved to the left or to the right. And when you move it to another cell to the left or right, what was in the target cell when you moved it is going to switch places. So if I move this don't care marker on the first row, if I move it over here to the left, well, that don't care marker will come here and it put the 1 there. And that entry is going to be don't care marker followed by a 1 for the next column and a 1 for the next column. And so I can shuffle the position of these don't care markers in every row of the table, and each position of the don't care markers, each setting across the entire table represents a particular configuration of the table, we'll call it. And we can therefore define a state space representing all of the configurations of the state table. This is our state space. And so when we think about the state space, well, if we take our don't care markers and we go down each column for each classifier, we would then train our classifier on those do care instances marked 1, and we leave out from the training set these don't care instances represented by having a don't care marker in that particular position for that classifier. So in this case, classifier F1 is going to train on inputs X1, X3, X4, and X6, and therefore the errors, or the so-called error budget, if you will, for classifier F1 is going to be X2 and X5 because they are excluded. And when you exclude a training input from training, you are depriving your classifier from the ability to correct its errors. And so, thought about differently, all of the don't care instances for each column of the table represent the error distribution, if you will, for each one of those respective classifiers. And so we have a selection table setting of the don't care markers, and each configuration defines one state in a large state space. And of course, once you train on the do care instances, you have a set of final best hypotheses, F1 hat through FM hat, for your component classifiers in the ensemble. And then you're going to get some model parameters out of that, resulting from an evaluation or training of the ensemble based on a particular state space within this large state space. And so we have as our state space the space of all possible arrangements that you can have for these asterisks, these don't care markers. And so let's define our state space. Big S consists of a set of states, S1 through SP. There are P many of them. And if we were to think of the complexity of the state space, well, in this particular case, it's quite large. So we have an M ensemble, and we said that you can commit floor of M over 2 errors. So our state space for a single row consists of M choose floor M over 2, many different states representing each of the M over M divided by 2, floor M over 2, many ways we can choose that error budget of floor M over 2 for an M ensemble. And that represents the row, a single row. Now, of course, for that setting for the first row, we can have M choose floor M over 2 settings for the second row, and similar for the third row and the fourth row. So this is multiplicative. And since we have n many instances, the size of the state space for a configuration table, given a data set of size n, is going to be M choose floor M over 2 exponentiated to the n power. Now, this is absolutely enormous, and it is exponential in the size of your training set, and therefore it's not feasible to solve it by a brute force. But we're going to evaluate this idea of a selection table and marking the error budget and using that as a way to get the coordinated training of component classifiers in an ensemble so that you can have direct control over their error distributions. And that's what we're going to use to introduce this idea of diversity to break shared biases between the component classifiers on this classifier jury. And so let's define the error associated with a single state for a state in our state space, our configuration state space for our selection table. And let EFS be the collective error for the ensemble that's trained from a particular state among your many possibilities in your state space. So therefore, our optimization problem, S star, is the optimal. It's going to be that state that minimizes the following objective. We're going to have a combination of the error associated with that state plus the diversity measurement associated with that state. Because at the end of the day, we want error diversity. We want the errors to be different from one another for the individual component classifiers in a way that we can break shared biases. And so the method I developed is called DISCO. DISCO stands for Discrete Instance Selection and Collective Optimization. And so let's proceed with how this DISCO works. And so it would be an absolute disaster to use local search. Things like hill climbing, randomized hill climbing, they use a fixed search neighborhood, and we could absolutely have mixed error independence objectives, the sum, but it can get stuck in local minima. And because the state space is so big, we want to try to have a more global view in terms of how we're searching the selection table state space for the optimal solution to get our S star. And so I used the genetic algorithm to find the best state table from a population of genetic fragments where each fragment represented a state table fragment. And so I called this algorithm GISCO-GA, and in this experiment, I had 5,000 generations, a population size of 50, and I did crossover. And when I did crossover, I doubled the population size using fragments from existing population members. I culled the top 50 solutions, and then I introduced a mutation rate, a change in the don't care marker of 1%. And the fitness function that I use to drive this DISCO-GA is going to be the accuracy based on a validation holdout from the training set. And so this is part of the training procedure, and it uses validation in order to evaluate this method. All right, so let's take our genetic algorithm. We have a population of state fragments. So we create our population, initialized randomly, and so we have selection tables that are configured with some state from our large state space. Then I score them. I train the ensemble using the do care instances, and then I grow the population by synthesizing new members proportionate to the relative score for two individuals selected from the previous round when I created that population. And so after creating the population, one of the things I do is score it, and I grow the population, and then I mutate. And so this mutation takes form as a probabilistic shifting of the don't care marker, either left or right, with some probability. And then after that, I rescore, and then I cull my population. So that I eliminate some number. When I grow it, I double the population, and then I cull it down to half. So the population goes back to what it started out with in terms of the number of members of the population. Okay, so I call this Disco GA, and in Disco GA, implemented it into my control systems framework. I have, of course, my plant, which is my ensemble method. I have my sensor measuring the error with respect to the ground truth label, target label, and that's for the output from the ensemble consensus opinion. And then I have crossover mutation scoring, culling, and the most fit selector for this approach using genetic algorithms. And so I evaluate fitness using validation error, because this is part of the training procedure for my method, and then I select the local minimum after each genetic algorithm round. And so I ran this on a number of the popular UCI machine learning data sets, the Wisconsin breast, cancer, iris, wine, Cleveland heart, glass, and dermatology data sets. And so I ran Disco GA, and I compared it against bagging and Ada Boost, and I also compared it against Random Forest. And the version of Random Forest I used axis parallel splits or linear combinations of the features instead of axis parallel splits. And so a random forest is a bagged decision tree. And with a decision tree, you issue a set of tests for your nodes, and these tests correspond to splits of the data set parallel to the feature axes. That's what happens when you choose a feature value and you say something like if some attribute is less than equal to some value. And so the random forest version that I used in this experiment did more than axis parallel splits. It used linear combinations of axes in order to draw or carve up the decision boundary. And so that was a much more powerful version of the traditional random forest. But nonetheless, I used that as well. And in addition to bagging boosting as the benchmarks against Disco GA. And so I used a number of different ensemble sizes, odd size number, 3 ensemble, 5 ensemble, 7 ensemble, etc., up to 40 ensemble. But here I'm just reporting something representative along the range of ensemble sizes that I tested: 3 ensemble, 9 ensemble, 15 ensemble, 21 ensemble. And for Wisconsin breast, iris, wine, and the glass data set, you can see that Disco GA beat the other methods with statistical significance. But for those cases where, for example, for iris and dermatology, Disco GA did not beat them so handily, but they were not statistically worse in terms of performance. So in terms of statistical significance, for iris and dermatology, the performance of Disco GA was not statistically significantly different. Okay. So part of the problem with the selection table, even with the genetic algorithm, is that it represents an entire selection of training inputs for all the classifiers in the ensemble. And so this is a so-called wrapper method. It's a black box, and you effectively train, or as I like to call it, evaluate the ensemble on a validation holdout from the training set. That can be very, very expensive because at the end of the day, you're training M component classifiers on that training set and then evaluating its performance on the validation holdout. And so the whole goal to speed this up is to avoid the ensemble evaluations. And so I looked for a so-called filter method that optimizes an alternate criteria for error and diversity, because at the end of the day, all I care about is minimizing error while at the same time improving diversity. And so if I can do this, which I did, I can get orders of magnitude speed up over brute force selecting your data and searching for it in an ensemble or rather in a data set. And this can afford you orders of magnitude of speed up over brute force, where that brute force is searching through the state space of all of those different selection table settings and evaluating the resulting ensemble. And so let's take a look back at the selection table. So let's recall the don't care instances. We said that classifiers do not train on the don't care instances. So these don't care instances are a proxy for the error distribution. And so essentially what we want then is to maximize the differences or maximize the diversity for component classifier error distributions. And in doing so, we can make them as different from one another as possible, which is what we're after. We're after this error diversity. And so in this case, the don't care distribution or error distribution for classifier F1 would be X2 and X5. For classifier F2 would be X1 and X6. And then we have X4 is the error distribution for classifier F3. And so let's introduce another construct, introduce a set of masks. And these masks, what I call don't care masks, are going to represent the assignment of do care instances and therefore don't care instances to the classifiers in the ensemble. And so a mask is a binary string, 0 and 1, that's k bits wide. And it just so happens that if you look at a particular don't care mask, you're going to have floor of k over 2 bits that are set. And what this don't care mask does is that when a position in this mask is non-zero, that corresponds to that particular instance being in the don't care set or being in the error distribution of that particular classifier. And so we have our mask mi, and we have a vector of the Boolean positions within the mask mi. We have mi1, mi2, and so forth. And so position in mask I, position j, or mij, takes on a value of 1 if for the ith input x, it's in the don't care set of the jth classifier cj. That position in the ith mask, mij, is going to be 0 otherwise. So the don't care masks identify the don't care instances, and we're going to use the don't care instances as proxies for component classifier error distributions. And so now what we set out to do is to create a stochastic process that will assign these don't care masks to all of the training inputs in our training set. And so as a process, our stochastic process applies a probability. It's the joint distribution between the inputs x and the masks m, the masks responsible for selecting the don't care instances. And so what this association does, this stochastic process, it's going to choose with some probability that a particular mask is going to be assigned to a particular training input, and that mask is going to become the entry of the selection table. And so this is based on some work called MaxEntropy for hypothesis formulation, and it's in the Annals of Mathematical Statistics from a long time ago, 1963. And so how does this work? It's based on this idea of maximizing the entropy in the distribution that you select when you're trying to build a stochastic process. And so essentially, what we're looking at is the joint entropy between our inputs from our training set, the xi, and the set of mass. So there's our expression for the joint entropy. And so now what we're set out to do is choose some probability p that maximizes the joint entropy between masks and inputs. And we're going to do this with some constraints. And the constraints are going to be based on the moments or summary statistics. The first moment is mean, second moment is variance, third moment is kurtosis, fourth moment is skew. And so, or skew is the third moment, and kurtosis is the fourth moment. And so, essentially, these equality constraints are on the moments between two quantities, the empirical distribution, which is over the data, and some model distribution, which we're going to select. And so essentially what we're going to do is we're going to treat the empirical distribution for mask assignment as uniform, and in doing so, we're going to make no assumptions whatsoever on the distribution for mask assignment. And so we have equality constraints on the moments between the empirical distribution over the data that we have and a model distribution that we're going to fit to this data. And so we treat the empirical distribution for mask assignment as uniform, and in doing so, make no commitments or assumptions beyond the moments. And so I designed a set of features and have a bunch of indicator functions, fj, and these fj's are parameterized by an input instance, xi, and a mask, mk. And so fj takes on a value 1 if mi, the ith mask, exclusive OR with the case mask, is equal to mj, and it's 0 otherwise. So what does this mean? So we have selection masks that respect the error budget for an ensemble for a given instance. And so what we're doing here is we're looking with this XOR for where these masks are different. So mask mk, where is it different from the mask associated with the ith training input xi? And that's going to be our mask mi. Now, what this is saying is that we have a mask associated with xi, and you can think of these quantities as the support set for a distribution, right? This distribution is a stochastic process that's jointly between inputs and masks. And so we can think of these as different support sets. So the mask associated with xi is responsible for a different part of the support set where this function takes on a non-zero value than the kth mask. And so this difference in support set is exactly the jth mask. And so essentially what we're saying here is that we want to spread out this support set, spreading of support. We want to spread out where this function takes on non-zero values. And if it's equidistant or spread apart in a nice way, then their differences are going to be incremental. And this is kind of like the idea of closure. Closure means that a set is complete. And in this case, our closure says how they are different is going to be complete. It's going to be spread out over all of the support of under consideration. And so the spreading out is really, really important because essentially what we want to do is make the error distributions associated with the component classifiers as different from one another as possible. And equidistant spacing, a part of error distributions, is the best way to make the error distributions for the component classifiers in an ensemble as different from one another as possible. And we're going to do that by spreading out the masks that are going to select the don't care instances associated with each one of the training inputs for the ensemble. Okay. And so in the literature, the maximum entropy distribution that makes no commitments is the Gibbs distribution. And the Gibbs distribution is just an exponential form. And that was published back in '57 by Jaynes, a famous statistician. And our model distribution is going to be this maximum entropy Gibbs distribution. So then the problem then is one to try to fit this Gibbs distribution's parameters to the data that we have, namely the masks and the training inputs. And so Q lambda is going to be our model distribution, and that's going to be our stochastic process for which we want to find the parameters. And it's going to be parameterized by xi and mk, so those are the two support set elements of our model distribution. And it's going to be 1 over z lambda, where z is a normalizing factor, e to the sum, and L goes from indexing over in that sum for the exponent. L is going to index over all of the possible error budgets, if you will, associated with the ensemble. So we said that we have k choose floor k over 2 many configurations for those floor k over 2 many don't care instances for a k ensemble. And so we have floor of k over 2 markers, don't care markers, and this k choose floor of k over 2 is the number of different configurations of those don't care markers associated with the ensemble. And so this is just going to be the sum of a parameter lambda times that particular feature. So we have an interpolated Gibbs distribution, which has contributing factors from our features that talks about the spread out mass, and we're going to weight them by these parameters lambda. And this is our Gibbs distribution. All right. And so what we're going to do then is we're going to minimize the distance between our empirical distribution over the data and this model distribution, the Gibbs distribution. Now, of course, we said Q lambda, and in this treatment, whenever we say Q, we mean the model distribution, our Gibbs distribution is shown here. And whenever we say P, we mean our empirical distribution from the data. Now, of course, this empirical distribution can be bootstrapped from the data using kernel density estimation, and then the Gibbs distribution has a parametric form. All right, so if we take the KL divergence between our empirical distribution P and our model distribution Q, this is just the sum of P of xi over the log odds ratio ln of P upon Q. And so we do the math there, and we get our second term here. That's the sum of P ln P of x minus P of xi ln Q. And we get that, of course, because the natural log of something divided by something else is just ln of the top minus ln of the bottom, and this P of x distributes to both of those terms. And so now, if we look at this expression, well, we get the first term. That first term, that's just the entropy of that probability distribution P, or empirical distribution, over x. And then the second term is the negative expected value with respect to P, this negative expectation of ln Q. And so what this second term is, this is just the negative expected log probability of our model distribution. And so entropy is going to be constant with respect to parameters of the Gibbs distribution, and we're going to minimize this negative expected log loss, which is this term. Negative expected, and when we say expected, it's the expectation with respect to our empirical distribution of that log Gibbs distribution, of that log model distribution. Okay, and this approach is based on some work by Phillips, Dudek, and Shapiri entitled A MaxEntropy Approach to Species Distribution Modeling from back in 2004. And so when we do this work for the negative expected log loss, so it's the expectation with respect to our empirical distribution, this tilde p, that's our empirical distribution of the negative log, expected log loss, and that's log of the model distribution Q lambda. And so if we calculate this, well, we have our expectation, so we're going to write our joint probability, probability with respect to empirical, that's P tilde, of xi ml over each one of the training inputs that we have in our data set and all of the masks that we have under consideration. And so here's our P, negative P of, is our joint probability. Now here's the log of Q lambda. So we have our log, that's 1 over z lambda e to that summation of our mixture with our lambdas and our features. Okay, and so if we do this expression, well, that's just our probability times log of 1 over z. So that's the probability of log z. Because this minus sign we can absorb here, that becomes z lambda over 1. And so we have here our probability, our log of our normalization factor z lambda, and then we also have our probability times the log of e to this exponent. And so log of e is just that exponent. So we have our minus probability, we have our summation, and we have our mixture of our features, which is just the exponent here, that e to that mixture of the features. And so we take this expression and we apply this summation to each of these terms, and we get the double summation of this first term minus the double summation for that second term. So here's the double summation for the first term. That's our joint probability, log z lambda. And here is the double summation for that second term, which is that double summation, our probability p tilde of xi ml. And here's our summation with our mixture of these features. Okay, and so if we want to minimize the KL divergence, that is the same as minimizing this negative expected log loss, which is the same as this expression. If this is our negative expected log loss, how we minimize that is by making this term as large as possible. And so essentially, we want to maximize this expected sum of our features mixed together for our Gibbs distribution, for our Q lambda. Okay, and so we're going to take this and we're going to put it in a control systems framework. And so here, our plant is the Gibbs distribution. This is what we're trying to manipulate. Our sensor is the log loss, and we want to minimize that log loss, okay, relative to the previous log loss. We want it to get smaller and smaller and smaller. We're also going to feed back some other measurements, the moments of this distribution. We're going to select the maximum from among these two, the error associated with the log loss, as well as the moments, because we have that constraint. And then we're going to update our feature weights, modifying our Gibbs distribution, and we keep doing that until convergence. And so the MaxEntropy framework estimates parameters for the Gibbs distribution. It represents the constraint search for probability distribution that selects, in our case, component classifier error distributions using these features for equidistant or spread out spacing, this kind of closure property that we talked about. And so here we have in this optimization equality constraints between the empirical distribution and the model distribution. And so this is the training procedure, call it MaxEntDisco, and you're going to input three things. You're going to input your training data. Here's our X. You're going to input your set of masks, and you're going to input your empirical distribution. Now, of course, empirical distribution, you can calculate that through standard methods like density estimation or through uniform assignment for values, but density estimation is usually a lot easier for your data. So we're going to repeat for some number of times for the number of mask types that we have for the error budget. We're going to take our feature values and we're going to compute them for each one of these feature values j. So we're going to randomly initialize our lambdas, and we're actually going to calculate this expected feature value for each of these j many features. And so then we're going to take the maximum for each one of these j features, for each one of these different mask types through expectation, and whichever one is larger among these fj hash marks, we're going to pick the largest one, the max. And so now we're going to update this max, and how we're going to update it is using some step, and that step is based on the log odds ratio. So here we have the expectation under the empirical distribution for that maximizing feature, and we have the expectation under the model distribution for this maximizing feature. So we're taking the proportion to say, okay, how much do these two distributions, the empirical distribution and the model distribution, agree on that particular maximizing feature? And so that feature itself is an expectation. And then we're going to also include the odds ratio for the opposite probability, 1 minus that model distribution, and we have 1 minus the empirical distribution for that maximum. And so we take this ratio for the opposite distribution, and we take the first ratio, and we put them together. And so it's the log odd ratio that represents the probability of that max as well as 1 minus that probability. So you're applying law of total probability here. And so based on that proportion, either you're going to get a value that's going to increase, alpha is greater than 1, or alpha is less than 1. And so we take that alpha, and we're going to say, okay, we're going to change our mixture weight, essentially giving our feature based on how much these two distributions agree, the model distribution and the empirical distribution, based on how much they agree in terms of the expectation of that maximizing feature, that's going to modulate how much we allow that particular feature to influence the Gibbs distribution. Okay, so this almost looks like an admissions probability in Metropolis Hastings, but it's just, you could think of it as the two-way likelihood ratio, and what you're measuring here is the coincidence between the first moment, the expectation, associated with the feature from the perspective of the model distribution, expectation with respect to Q lambda, and the empirical distribution, the expectation with respect to P tilde. And so you do your update based on that coincidence. How much do the model and the empirical distribution agree on the expectation, the first moment, associated with this feature? So then once you calculate that update, that's the new lambda, and then you recalculate your negative expected log probability. You reevaluate your negative expected log loss. And so your negative expected log loss, well, you just recalculate using that new lambda, and this is just what we had before for a Gibbs distribution. You have your P, your joint probability times your log, so your expected log normalization factor, minus your joint probability, that's your expected mixture of features. And then once you update your negative expected log loss, you look to see how it's changed, and you keep this process going again and again and again until the change in the negative expected log loss is negligible. And after that, you return what your Q lambda is, which is your Gibbs distribution, now that you have all those features. And again, your Gibbs distribution is defined here. All right. So once you've done that, that is their training procedure. You now have a Gibbs distribution with the correct parameters that maximizes the entropy with the empirical distribution, but also make sure that the moments are the same. And those moments being the same are enforced by this line number 7 in your algorithm. Do they agree on their expectations? All right. And so this is what I call MaxEnt Disco. We have that training regime. So now we're going to sample from our distribution, our Gibbs distribution, now that we found parameters for it in the training procedure to assign the mass. So you input your training data, you input your Gibbs distribution, Q lambda, and you build a selection table from your training set. So for each one of the training inputs, you're going to get the training instance for the ith row of your selection table, and then you're going to sample from this Gibbs distribution given that particular training input. You're going to sample a mask value, and then you're going to set the ith row of your selection table to that mask that you sampled from your Gibbs distribution, and then you're going to keep going. So then once you've done that, after line 8, after this loop between lines 4 and 8 has iterated to its completion, and many times, one for each one of the training inputs, you're going to have a selection table that's populated with masks, and then you go ahead and train the ensemble by excluding the don't care instances that are selecting by the mask that you've set for your selection table key. All right, so this is Maxent Disco. Let's look at some experiments that I had done. And so I created something I call a noisy alternating ring. So it's a two-class problem. We have the red class and the blue class, and I put them equidistant around an ellipse, and then I measured the variance, and then I increased the variance some integer number that I call the dispersion. And so as you increase the dispersion, these point clouds get more and more interleaved, getting more and more difficult. And so I tried a dispersion from 1, multiple of 1, all the way up to 40, but I'm just not showing you all of them. And so here we took our noisy alternating ring, as I call it, and this is a synthetic data set with dispersion ranging from 1 to 40. It's a 2D feature space. I have 1,000 instances with uniform priors, and I use tenfold cross-validation. I implemented this in Java as part of the Weka data mining toolkit. The base classifier for this Disco ensemble is C45 decision tree, which is called J48 in Weka. And then the convergence criteria for the training regime for Maxent Disco is that the change in expected log loss is 0.0001%. And then I tried this on multiple size ensembles, but I'm going to present to you 3, 11, and 21 ensemble. And this represents low, medium, and high. I actually did 1 through 21 in the full set of experiments. And so this is Maxent Disco, one of the results on synthetic data, the noisy alternating ring. On the horizontal axis, I have the dispersion. On the vertical axis, I have the accuracy. So higher is better. Now, in the red is bagging, the green line is boosting, and the blue is Maxent Disco. So as you can see here, Maxent Disco, it outperforms bagging and boosting from small dispersions on through medium dispersions, right until we get to something that's much more difficult around 30. We see that Maxent Disco starts to fall apart. But for the most part, you see that it does competitively well against bagging and boosting. If we look at this is for 3 ensemble, let's look at the 11 ensemble. Now, as we increase the ensemble size, we see that Maxent Disco kind of hangs on longer, but you see that boosting really starts to degrade around a dispersion of 20. But bagging is doing okay. And in fact, bagging at some point surpasses Maxent Disco with statistical significance. But Maxent Disco does well for small dispersion up through medium dispersion for the 11 ensemble. So let's now look at the 21 ensemble. For the 21 ensemble, it's a similar behavior, right? We see boosting, it fails and starts to do very poorly as you get to around 25, 30 dispersion as the problem gets more difficult, more interleaved. And then we see Maxent Disco does particularly well for low dispersion, and then it holds on right around 27 or so dispersion. And so this result holds that Maxent Disco is very competitive, and it actually beats, for many of the cases, most of the cases, the performance of bagging and boosting. And it's not until we get to very confused data, right around 27 or greater dispersion, that bagging or boosting tend to pick up and perform better. And so, but one of the key observations here, yes, Maxent Disco outperforms bagging and boosting with significant for low to moderate difficulty for small and medium-sized ensembles, and even for the larger ensemble 21, it does well for about at least half the time for difficulty. But the key takeaway here is that you'll recall when we built the selection table, that selection table, when we selected the error distribution, that error distribution consisted of at most 1 copy of the instances. Moreover, when we trained the ensembles using Maxent Disco, that selection table trained those component classifiers with at most 1 copy of each training input. This is in contrast to bagging and boosting, where we use sampling. And when you use sampling, you can have multiple copies of your training inputs. Now, in essence, when you think about what happens when you are searching through a hypothesis space to correct for training errors, essentially, if our hypothesis were linear, and let's say we had all the plus points here, and we had one error, this minus point, and then we had all the minus points here, and we had one error, let's say the plus points. When we are training, you can think of this changing the hypothesis as this training input essentially attracting the decision boundary when you're selecting a new one. Now, certainly, this one is going to want to pull the decision boundary towards it, and this one is going to want to pull the decision boundary, that other part, the top part, towards it, and in essence, select a boundary that looks like this, that's more up and down. And so you can think of each training input as almost like a magnetic particle that wants to attract a metal decision boundary towards it. It's an attractive force. And so the more copies of a training input you have, the more powerful your attractive force will be in selecting for a different hypothesis and moving that decision boundary as you go from one version of the hypothesis to the next, one working hypothesis to the next. And so because bagging and boosting have more than one copy of the training inputs, they can exercise their decision boundary movement in a far more sophisticated way. But nonetheless, even though MaxEntDisco only had a single copy of the training inputs, it still, as we saw, beats boosting and bagging that were more expressive, if you will, in most of the cases. And so I'm certain that if MaxEntDisco had to its availability more than one copy of the training input, that this improvement would persist throughout all of the complexity of the data set. Okay, and so let's take a look at what I concluded. You can deliberately build diverse ensembles, and this is the important part in my main contribution, by coordinating the component classifier errors, and you can do so, moreover, as an optimization problem. Now, in this approach, it can outperform state-of-the-art, which was state-of-the-art at the time, using only a single copy, and that's important, a single copy of each instance. And this is in contrast to methods that are sampling-based, that are randomized sampling-based, that have to their availability more than one copy. And so MaxEntDisco is very effective when classes overlap moderately, and it contributes a new method for ensemble construction as a density estimation problem, this estimation of the Gibbs distribution, or MaxEntropy distribution. MaxEntDisco then uses diversity or entropy to do the work of building the ensemble. And this is the main contribution of this particular work. And so some of the limitations, the implementation that I had for my thesis for the selection table assumed you only had a single copy and majority vote. Right? Very simple, gives you powerful results. Now, the selection table initially, the state space is exponential in the training set size. Now, that was just to demonstrate the method, of course, because it's exponential. You'd never use it in practice, but the GA was just a proof of concept to show you this idea of coordinating the error distribution is sound, which it demonstrated. Now, the MaxEntDisco implementation that I contributed, it only considers the sampled mass for the maximum error budget, but it doesn't look at less than maximum, the minimum error budget onto the maximum. And it also need better density estimation for anisotropic distributions. And so for my density estimates, I use kernel density estimation for the empirical distribution using the diagonal terms and not the off-diagonal terms, which would give you much better density estimates to further improve the method. So that's Disco, and that was my contribution for my thesis. And future considerations, active Disco to score and select the inputs based on their contribution to diversity and incorporate them rather than in full broad brush populating a selection table. To have the selection table version or approach that includes more than a single copy of each instance. And then an approach for estimating off diagonal terms for density estimations for the covariance matrix, plug-in estimators for non-parametric density estimation. And then also need something that's really, really fast for it to be even more practical. Granted, the filter method works really, really fast, works really, really well, but to try to get even further performance improvements. So those are future considerations. Didn't get to all of them, but they're there nonetheless. And so with that, we'll end there. And as usual, please stay healthy, stay safe, have a happy Thanksgiving, and I will see you all on Tuesday.